So now let's solve the factorial function with recursion. So I'm going to write define f of fr of n, fr meaning factorial recursively. And then here, if n equals 1, we're going to return 1, else return n multiplied by factorial function of n minus 1. Okay, that's all that it is to write a factorial function recursively. To help us understand what's going on here, even though this is all the code you would write in your text editor, Sublime, or whatever it is to write, to run your code, we're going to go ahead and make copies of this function just like before in our more general example so that we can understand what's happening in each case. Okay, so I'm going to write define fr prime of n if n equals 1, return 1, else return n times fr of n minus 1. And then I'm going to write define fr double prime of n if n equals 1, return n times fr of n minus 1. And I'm going to say, this one calls this one calls this one, and this one will call another one. So define r of triple prime of n, where if n equals 1, else turn n times f of r of n minus 1. Okay, and so because we're using 4 factorial previously, we'll do that again. So we'll say n equals 4 here. We'll say n equals 3 here, n equals 2, and finally n equals 1 here. And that's because in this factorial function, we are calling ourselves. I can write my T diagram. Okay, and then I'm going to write n, and then write r for result. Okay, r is for result. N and r is for result. N and then r for result. And r for result. So n equals 4 here. Because n equals 4, it does not hit this if statement condition, but rather it simply returns. And it's going to return 4 multiplied by the factorial function of 3. So we know that n is 4, but we do not yet know what the factorial function of 3 is. So this is going to be pending for now. Okay. Now we call this the factorial function of 3. So here n is 3. Again, this if block does not run, and it said that it's going to return n multiplied by the factorial function of 2. Well, we don't know what the factorial function of 2 is, so it's going to call itself, or rather a copy of itself. It's assigned n to 2, and again, it's going to return 2 multiplied by the factorial function of 1. Well, again, we don't know what the factorial function of 1 is yet, so it will call another copy of itself. Here, n is assigned to 1. Now finally, because n is 1, we're able to hit our base case. And in our base case, we say that if n equals 1, we can return the value of 1. So our result that's returned is 1. This 1 is returned to here, which is then multiplied by n being 2. So that gives us a result of 2. And this result of 2 is passed back to here, which is multiplied by n again, n being 3 here, and so that result is 6. And then this result is passed to here. And this 6 is multiplied by n of 4, which is 24. So this is our factorial function with factorial function done recursively. Okay, so I want to talk about a few different trade-offs as we compare this example of solving the factorial function recursively with our previous example of doing a factorial function iteratively. Okay, so here's the trade-offs. So one of the benefits of doing things recursively is the code is actually a little bit simpler. It may be a little harder for you to conceptualize at first because you're not used to doing things with recursion, but there's actually less lines of code. If you compare this one with the previous one, this one has less lines of code. And it's actually a little bit simpler to write once you get the hang of recursion. So I'm going to write simpler. Now this is particularly true actually when you start getting to more complicated examples. So you can solve a lot of different problems recursively, and sometimes the only way that you can think of how to solve a problem is actually through recursion, and it's much difficult to solve a problem through iteration. Okay, drawback of using recursion: because we have all of these different stack frames in play, at the point that we reach our last stack frame, these stack frames are still being held in memory. So what that means is there is still a spot in memory that's being tied up by assigning n equals 4, and another one tied up by assigning n equals 3, n equals 2, and then also n equals 1, and then we finally assign a result of 1. So at the same time, you have 5 different things that are in memory. Okay, now in our iterative case, at any given time, even though our n and product values were changing, we only ever had those 2 variables that were being assigned in memory, and then one was getting overwritten. The n value would get overwritten with a new value, and so with the product value. So this one takes more memory. 4 integers is not really that much memory, so it's okay to write a recursive case like this. But if you have other examples where you're going to be calling yourself a factorial function is going to call itself a lot more times, then that memory space can add up. And also, if inside your factorial function you are actually assigning, say, an array or a lot more other variables, then that will also add up as you have more calls and more variables being stored in memory for each call. So you have to keep that in mind when you're writing recursive functions and make sure that you're not using an excessive amount of memory. Okay, so that is pretty much what a recursive function with factorial looks like. I'm going to go over the summary points one more time, and that's because again, the summary points are the keys to understanding recursion. So I want to have us review it with this factorial function. So again, a recursive function is going to call itself. So here, in this factorial function, we are returning n multiplied by the factorial of n minus 1, so it is calling itself. In addition to that, we have a base case. Our base case is this section, base case, where if n equals 1, we're going to return 1. And so it's a base case because it's able to evaluate to a result without having the function call itself when the variables fit that base case. And then we're making forward progress towards the base case. Forward progress towards base case. So as this factorial function calls itself, n is getting decremented, and because our final n is n equals 1 for the base case, 4 is getting closer, the n is getting closer to the base case as it goes from 4 to 3 to 2 to 1. And as I said earlier, the base case does not have to be n equals 1. The base case could be another number. If it was n equals 2, this function would also evaluate, though it wouldn't exactly be a factorial function. But also, even if n was a higher number, like 10 or 100, if we were starting with n equals 4, we would just have to make sure that we're adding, when the factorial function is calling itself, we're calling factorial of n plus 1 instead of n minus 1, so that we make progress towards that base case. And finally, we have different n's. Okay, this is one scope, but when the factorial function calls itself, we are in yet another scope. And in another scope, each variable has a different value, even though it may have the same name, just as in the original example with function A and function B. So these are the important things to keep in mind when writing your recursive functions. Make sure you keep these different things in mind and you write accordingly to it, and you should be able to solve problems recursively. And that covers our lecture for recursion. Thank you very much.